Good Monday evening. Welcome to the Land Tamer stream. We're starting off a little early tonight. Normal schedule is about 7 p.m. Eastern time, but I've spent a good bit of time today studying some spanning tree, multiple spanning tree, and just figured let me get started a little early. So it's been a good weekend for labbing and studying. So hope everyone's doing well. This wallpaper of the day is another nebula. If you notice a little cloudy region in here, it's really wild, but that's from the Hubble. And it is little known nebula IRAS 05437 plus 2502, courtesy of nasa.gov. This is a NASA image of the day. Cool stuff. Hey, we got mentors, we got Callum. Good to see you, my friends. Hope you're having a good day as well. Monday, starting off the week with the day off here in the U.S., which is awesome. Yeah, it does. It's some weird. I mean, all kind of stuff going on there. So just a couple of vlog topics before we do a lab, and we're going to actually review some Ethernet addressing stuff. One is talking about the exam itself. I did take some time today. We did some sort of family planning, vacations, holidays, stuff like that. And I went ahead and committed. I'm pretty much committed to this next date, even though I moved it once because they emailed me and told me I had to. So I'm 56 days out, but, I could still move it again. It's not like I won't if I'm not ready. But for the written exam, I went ahead and took, like a lot of companies, you have to use a certain number of days or you lose them at the end of the year. So, after summer, I like to make sure and check that I'm not going to lose any days, paid vacation days. So I went ahead and took Anyway, I'm going to have 6 days off prior to the exam day, which is a Monday. So I'm going to have Wednesday, Thursday, Friday, Saturday, Sunday off, and Monday, of course. So that's my game plan right now, gearing up for that, not forgetting, it's 56 days, still a lot, but still, it'll be here before we know it. Also, Github Updates, I did clean that up a little bit. So now if you go to GitHub and if you clone to the repos, the agenda streams is fixed. I'd fallen a couple days behind on that, and the captures. So I basically deleted them off Google Drive, and they're now all on the GitHub site. So I think I have 4 repos up there now, but just getting started. But they're there. And speaking of PCAPs, so this is awesome, folks. This was, I had a couple of responses to this about dummy multicast frames and uplink fast. And finally, I think Peter Palick took some day from his holiday to help out the community, the networking community. And he went and labbed up using some real switching gear to produce these Ethernet dummy multicast frames. We're going to look at them here now. You planned that out quite nicely. Yes, thank you, mentors. Try to do that. I'm a little bit of a planner, sometimes a little too much. I need to roll with the flow more sometimes, but in this case, yeah, All right, so this is VS Code, and I'm still learning about it, but I was hoping I could just go to, I'm in an edit mode, but I thought VS Code would know that this is a link that I want to go to. If I'm missing something there, let me know, but all right, so this was, I'm not going to share the entire tweet storm or whatever, but I think it was Sunday. I was like, okay, I haven't been able to find this. I haven't gotten any response. If anyone has seen these, it'd be great. And then, Peter Palick, who is the author of, he is one of the co-authors of, I think, Volume 1 of the official certification guide. I met him in person. He did an EIGRP, at the last Cisco Live, he did an EIGRP session, which was the bomb. And he's just a very smart and very nice guy. And it was nice to meet him in person. But essentially, he reached out, I think, Sunday and said, look, this is the link you need. This is a real thing. This is how you reproduce these frames. And I replied, well, does anybody have these? Because I haven't found them on the internet. I don't have access to this gear that I can just lab on. real gear, and it is a proprietary protocol. So he tweeted out, people are like, what are you doing on your day off? He's like, well, capturing uplink fast multicast proxy frames for the land tamer. And he actually shared them out at Wireshark. So the link is here, and we're going to take a look at them. It's one of those things where curiosity, killed the cat. And maybe that's the case here. But if you look under Wireshark's sample captures page, this is like a nice little museum of, we need a museum for packet captures, right? So he's got spanning tree protocol. This was already here, I believe. So Peter loaded this one, STP uplink fast. And description here is Cisco STP uplink fast proxy multicast frame sent to this address. This is exactly what I'm looking for. This file contains a capture proxy, also called dummy multicast frames. Now, proxy is a new name for it for me. I had not heard that yet. I don't think. These multicast frames sent after a root port switchover on behalf of 3 dynamic unicast MAC addresses to update the upstream part of the network about the new path toward them. For each of the MAC addresses, there are 3. The switch sends out 4 frames using a particular MAC address as a source. So as we can see, that's why it's proxy, right? The switch is originating the frames, although it doesn't own those. That's kind of cool, right? So it doesn't own those MAC addresses, but it knows about them, and it's going to sort of spoof. I've heard spoof, I've heard proxy, I've heard dummy. So anyway, the switch sends out 4 frames using a particular MAC address as a source, and this special address as a destination, with each frame using a different type of snap. Okay, so these are the 4 different ones using a different type. You got snap, AppleTalk, EtherType, and ARP. Okay, that explains it. I looked at this earlier. I was still a little confused. The frame payload is just a stuffing to the minimum frame length. It has no meaning. This is beautiful, folks. I love it. The call went out to the Twitterverse and was answered. So let's take a look at these frames here. And here we go. Check it out. So here's the destination. Now notice if we look at the destination address, it is this mysterious 01000C, which is, we're going to break down these bits in a minute. Basically, you see 0C, that's Cisco. This is awesome resource. I never knew this even existed. Yeah, I've been here multiple times because I'm on this kick where, when I see or read about something new, I want to see the packets. I want to see a capture. And generally, I try not to take the time to have to produce it myself unless it's just curiosity. Usually, I'll Google search and they'll come to this page. There's a couple other really good archives out there there's some security sites that have like a bunch of PCAPs from different signatures and things like that. But this Wireshark, wiki.wireshark.org has a lot of, more network engineering type PCAPs out here. So usually I just come here, I'm able to find the capture I want, look at it under the microscope, like, okay, cool. I've seen it. I've looked at this microscope slide. I'm good. I don't need to lab this to save time. But in this particular case, I couldn't find this one. So the frame payload. All right, so let's take a look at one of these. Let's kind of follow along with what Peter wrote here. All right, so this is a destination that we've been looking for. And the source, in this particular case, I'm assuming... All right, let me see what he says here about the source of the... For each of the MAC addresses, the switch sends out 4 frames. Okay. So this is one of the MAC addresses that the switch is spoofing. I just usually look at the last 4, right? D740. All right, there's 4 for each, right? D740, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Awesome, perfect, just like he said. So let's look at where this is destined to. We see the destination address, but what does the LLC tell us? All right, this normal destination snap and source DSAP and SAP. Cisco PID is unknown. Okay, this is just the snap version. And this is just padding data. This doesn't matter, right? Cool. So this would forward to the this would forward to the switch immediately upstream. So it would know about them. I wonder so let's say in this topology, for example, we have a direct link failure. That's where we use uplink fast, right? It's for direct link failures. And this goes down. So switch 4 would send a dummy Ethernet multicast or proxy Ethernet multicast proxy frame up this way. And switch 3 would now learn about H1 here. Would he forward these, though? I don't think he would. He might, though. If it strictly adheres to the rules of multicast, I guess he would. Yeah, okay. So go up to topology. But this is one protocol type, which is SNAP. Service Network Access Point, right? This is another interesting datagram delivery protocol. AppleTalk, yeah, 809B is the Ethernet type. Interesting that there is no Ethernet type defined here. It just uses LLC. Our destination is the same. And it's interesting that Wireshark recognizes this as STP uplink fast, right? And it says malformed packet. That doesn't really matter. Cool, so uplink fast by default is going to send an AppleTalk frame. All right, then we have this one, which is NetWare. Cool. IPX, SPX. The type there is 8137, and then we have ARP. Interesting. This is a protocol. This is an opcode 277. ARP opcode address opcode 115. And then sub opcode 277. This is interesting stuff. So there it is, folks. RTMP, LLC, RTMP, IPX, and ARP for each of these. That is too cool. Thank you so much, Peter. I realize you may not be watching. I thanked you on Twitter, but man, curiosity satisfied. That was a nice contribution to the community. We really, really appreciate it. So there we go, folks. Mystery solved. And speaking of that, I'm going to move this down because I want to talk about that once we get sort of into labbing. But let's talk about these Ethernet addressing. You know, yesterday I was looking at the drill sheet, and let me go and pull it up. I don't think I have it here yet. I've switched from Brave to Firefox for the stream. I need to bookmark the drill sheet. There we go. If any of you noticed yesterday, I referred to this drill sheet and these multicast, Ethernet multicast addresses. And my curiosity was kind of piqued today when I looked at this again. Let's bookmark that. Drills. Doesn't load a lot faster, but it does seem to load a little faster. Okay. Here we go. Multicast Ethernet addresses. So I was looking at this earlier today. I'm like, okay, I missed a little quiz myself yesterday, and I did 0-1, and I got the first two wrong on one of these. But I noticed, all these are 0-1s, right? Until you get to some of these here, ISIS, and then you have IPv6 multicast map, which is 3.3. And these first, of course, this is part of the, that the first 6 hexadecimal characters are the OUI in most cases, not always, but generally that's the organizationally unique identifier part of the address. Then you have the end station address is the last 6, right? There's 12 that make up an Ethernet MAC address. But there are a couple bits here. The first 2 are important. And even though they're part of globally assigned, prefix, they do mean something. And I saw that when I started looking at these PCAPs. So let's take a look, for example, let's break down what this would mean. And I'm going to open up this in Wireshark. Actually, the one we just looked at is fine. Because you'll notice in Wireshark, for example, the way it pulls these out is when you look at the 802.3, these are 802.3 frames. And the destination address, you'll notice it always calls out these 2 bits, right? So when you've got 12 hexadecimal, let's break this down, right? What are these? Why is it calling these bits out? What does this mean? And as you can see here, it's saying this bit here is a LG bit. And LG is either locally significant or globally significant, I guess. Locally configured or globally unique. It's either L or G. If it's a 0, it's a globally unique address. If it's a 1, it's a local. So think about, for example, if I were to change my burn-in address. Oh, I need to turn off my little timer here. I need that right now. If I were to change my burn-in address, you could do that. You might do it like with HSRP or something like that. Or you might just be trying to spoof something. Well, then you should use a 1 here in this bit to signify that this is a locally administered or locally configured bit. That it may fail on the internet because it might be used by someone else. That's what that bit means. And as you see, it's the second to the least significant bit of this first byte. These are 8 bits, right, of the first byte. And it's the second to the last. The last bit here is I or G. So is it a independent? Or is it a group address? Group address meaning just multicast, right? So independent means unicast. So a 0 would be a unicast address, and a 1 would be a group or a multicast address. So let's see how that would actually break down here. I've got some notes. This is one I did the other day, which was the DECNet MOP-remote-console. And it started out with AB. I'm like, how does that fit in, right? So what you do is you take your hexadecimal bits or characters, and this is the way I do it anyway. You convert the hex to a decimal, right? So A is 10 and B is 11, right? So then you take the number 10 and you can convert that to binary. So 10 and 11, 10 is of course 1, 2, 4, 8. It is 8 plus 2 is 10. And the 8th place bit here is a 1. The 2 place bit here is a 1. And the 1's bit is a 1. So that's 11, right? So if you put these together, that's your first byte of the hardware address. And then here we go. So we look at the second to the last bit is a 1. That is local. So it turns out that DECNet, and as a matter of fact, you can do, you know, routing in DECNet, and you can assign sort of, I guess, like, it's not globally routed. In other words, it's only locally significant if you're using a DECNet address, right? And in this case, for example, that's not the really important, but you have the last bit, which is individual or group. This obviously is a group address. You're trying to, it's basically being broadcast on the segment in the hopes of finding anyone listening on this multicast address. So the IG bit is set to 1, meaning it's the group. It's a group address. So that's how that works. That's how you break it down, of course, from hexadecimal to binary to hexadecimal to decimal to binary. But you've seen some of these already, really, like 000, that's like global individual. So you see this a lot. The first two, you see 01, like the majority of those were 01 because it's global and it is a group or a multicast address. In fact, I think I already closed it, but you get the idea, right? Yeah. Most of those are 01s. And again, that doesn't mean that there could be other combinations of that, right? Because we convert the hexadecimal. There are other combinations that would work. But let's see, let's go. This thing is so big. Yeah, so a lot of these are 01s for the first 2 bits because they're multicast. And then if we go to 3.3, we can do the same here, right? 3 in hexadecimal. Actually, did I do this right? Yeah. So 3 in hexadecimal is 3 in decimal is 0011 in binary, 0011 in binary. So as you can see, the last 2 are 1 and 1. So it's a local. And remember, 3.3 is what? It's IPv6 converted to IPv4. So there's not really a chance for that to be necessarily globally unique. So, and Siri thinks I'm talking to her. But, so that's why that would be locally administered, right? Or locally significant. And then, of course, it is a group. So 1.1 is at the end. So as we can see here, even though 1.1 is B, 1.1 is also 33. Turns out to have those bits be the same. All right, another tweet just to vlog about is STP path selection. This is a cool tweet. There was some conversation on Twitter about, you know, what are you doing today? I'm working on MST, multiple spanning tree, and I'm working on this. And I'm like, oh yeah, spanning tree, I need to get better at that. So it's kind of how that conversation went. But I linked it here because Waxtrax, who is a great contributor to the community. Oh, command click. It does work. Sweet. So he made this comment, and I wanted to elaborate on this. This is a good way to think of it. He's like, the biggest difference for me was remembering STP cost influences the path towards the upstream switch, and poor priority influences the path towards the downstream switch. After getting that down, everything else clicked for me. And we talked about this on the stream the other day when we talked about the criteria, right, for selecting the root port. First, it is the cost. So the cost is always transmitted down the path. So this switch, when he sends a BP to you, if he's root, it will get to switch 2. Switch 2 is going to add his cost down to switch 4. The cost will be 0. I believe that's how that works. And then switch 2, when he sends his BPU down to 4, he's going to add his cost. So the cumulative cost is used by switch 4 as the first criteria to determine the shortest path, or which interface to use as its root port, right? But if there is a tie, which there is in this case, for example. So let's look at switch 4. Let's just kind of walk through this. Show span. We only have VLAN 1 on here right now. So he has 4 active non-edge ports. And notice, to prevent a loop, of course, 3 of them are blocking and 1 is chosen as the root port. These are blocking and are alternate ports, right? This is designated because it's going down to a edge port. This is the host 1 and he's running port fast. So how do we know the selection? Well, if we look here, we see that we likely had a 4-way tie. And if we look at just the topology here, so he would have gotten 2 from switch 2 and 2 from switch 3. And notice he has selected GI02, which is going towards switch 2. Again, first priority, the cost should be the same here for all the links. Let's see. This does not show the cost here, does it? Oh yeah, it does. Yeah, my cost to get there is 8. That's 2 gigabit interfaces, I think, of 4, a cost of 4 each. So he knows the costs. They all tied for the cost. Then what's the next selection criteria? It's the sending bridge ID. So when switch 2 sends to switch 4 and switch 3 sends to switch 4, switch 2 is going to have a lower bridge ID. So let's look at let's do on switch 2, show spanning tree. And let's go to switch 3. Show span. Let me make sure I'm saying the right thing here. We know that their priority is going to be the same. But yeah, the bridge ID is technically the priority and the address together, right? So it'd be 52769.5000.03.00. This would be 002. So the lower bridge ID or bridge priority wins. And so that's why switch 2 is chosen. Now with switch 2, I've got 2 ports. So what is my third selection criteria? It is the port priority. And here we see that the 2 ports going towards switch 2, GI02 and 3, have the same port priority. The lower port priority, generally this is lower. Anything lower is better with spanning tree. And then then it goes to the 4th criteria, which is the port number. And GI02 has a lower port number, right? So let's say we wanted to influence that on, let's go to switch 2. I have kind of a similar situation here, right? So if I do, like it is, show spanning tree on switch 2, my root port is GI00, and then GI01. So I have 2 ports. These are designated because I probably in the beginning, well, since switch 1 won the election, and I know that these are superior BPDU coming this way, because even though this gets relayed from switch 3, actually, where's this coming from? GI02. Okay, this is going down to switch 4. So even though, let's say in the beginning, switch 4 may have relayed some BPDUs this way, I would have known that these 2 would have come down to either of these 2, because this has a superior bridge ID, right, than switch 4. And the cost would have been better anyway. It would have won it over cost. So it would have come down to cost. It's the same bridge ID sending bridge ID. Then it goes down to port priority, which are the same, and then lowest port number, which is 1. Now, if I want to influence my upstream, as Waxtrax was saying there, is I would need to, adjust the cost. Because you can't really adjust, or I would not recommend adjusting or trying to adjust the bridge priority. And in this case, it wouldn't matter because, it would if I had, it would in the case of switch 4, right? I could influence it that way, but I would not really recommend that because that affects the entire topology when you're changing the priority of a particular switch. We're trying to influence the link priorities here, right? So what we're going to do is we're going to say, also, so on the bridge priority, if I lower this to 327, well, I'd have to go in increments of, what are the increments in 4096, I think, right? I would have to go lower, and then I would have to lower the routes as well to make sure it's still lower than switch 3. So that's not a clean way to do it. The best way, if I want to influence my upstream traffic here, instead of using GI00, I'm going to lower the cost or increase the cost of one of the other interfaces. So one easy way to do this would be on interface GI00, spanning tree. I don't remember the, just cost. And let's just increase it. So right now the cost is probably 4. Yeah. Let's just say 20. Now let's do show spanning tree. All right, so we've got a transition here. We've made a change to the topology. So, and we're running classic spanning tree, so this is going to take a minute, just about literally. So we went from listening to learning, now it should go to forwarding. Here in a second. Still learning, now forwarding. So there we go, the cost here is higher, so this is now preferred. That's a good way to influence the upstream. Now the downstream, as we mentioned, we can't really change the we could change the cost here, but let's say we want to make all our changes on switch 2 closer, as close to the root bridge as possible. Or maybe that's what our design calls for. So we're going to say on switch 2, what we're going to do is adjust the port priority. And actually when switch 2 sends his two BPDUs down these designated ports, he's going to see the designated ports here. He's going to include that administratively configured port priority. Instead of 128, for example, we're going to make one of them lower. And then that will influence downstream which port that switch 4 is going to select as its root port, right? So let's say there's GI0. I think 2 is going to be in use now. So let's increase it. Spanning tree, port priority. It has to be increments of 32, right? So right now it's going to be 128. Let's add 64. And so that'll be 192. Let's go to switch 4. Okay, it still is not seeing the priority here. Okay, let's take a look at our BPDUs. I don't know if we have to have, I seem to recall, did I change the right port? GS02, yes. So there's the port priority. That should influence switch 4. Maybe this requires a topology change. Let's see. Let's go capture here. We're going to capture on J02. Let's look at these BPDUs. Let's see. So yeah, this is what's coming in on this interface, right? The root path cost is 4. Bridge priority, bridge system ID, port identifier is 3. Okay, this is on our PVST. Yeah, you know, I don't see that field on here. Topology change is set, by the way. Aha, okay. This is why I wanted to lab this, because I was not 100% sure about his statement. And I wanted to come in here and just check. Yeah, I don't see any kind of... we have a root path cost. Message age, max age, hello time for delayed, all that. Yeah. And as we see here, it's not really influencing. That appears to be a locally significant value, doesn't it? All right, let's just leave it like that, and let's change the port priority here. Oh, wait a second. Show span. Okay, it did change it. It did change it, but how or why did it change it? All right, let's do this. Let's debug spanning tree events. Yeah, because before it was J02, wasn't it? Yeah. I probably just got impatient. There we go. There we see the learning. Okay. All right, that's what I was expecting, but I was also expecting in these frames some sort of communication in terms of the port priority. And I'm not seeing it. Let's look at PVST plus. Oh, I need to monitor the other port, don't I? That's the problem. That's my problem all along. GI03, yeah. Let's see it over here. Okay, let's just do STP. TCN is off. The root identifier. Yeah, the identifier, that's for the root bridge. The bridge identifier. Port identifier is number 4. Right, how is that port priority being communicated? Let's look at all. Trunk type. Sender ID. I'm a little baffled by that. All right, let's do it again. Just like kid, do it again, do it again. Let's see, interface. GI02, no span, port priority. No spanning, oh. Spanning tree, port, priority 128. Okay, sent topology change notice. New port ID 8003. Oh, is it via this port ID? Port ID here is C003. Oh, it's in this field, isn't it? It's in this field. Yep, it's got to be. Aha. Yep, and it went and made the transition. Okay, so that's where it is. And why am I not seeing my... Not seeing any frames here. Because it's just blocking, isn't it? Okay. That's okay. We're going to transition back in a minute. All right. So right now, the port identifier is 8003. So this must be the priority 80. And this is the port number. Actually, I'm not sure how to interpret that. Port identifier 8003. What happens when we shut down this port? Phase 0. I'm capturing the wrong port, aren't I? GI03, capture GI03. Port identifier 8004. I think 80, so 80 would be what? It would be in hexadecimal. $128. Aha. Okay. That's how it's communicating it. Okay. You know, I probably knew this. Okay, then when we get back here, I'm sure I reviewed this in the past, but that's why we're reviewing it again. Yeah, 8003. Okay. Cool. That's why it was C0 before, right? It was 192. All right, good deal. So that, I just want to bring out this statement. That was a cool way to kind of summarize it. And I verified it now. That indeed, you know, those are the traditional ways you would influence upstream or downstream traffic based on which ports you want to use. All right, let's do a little lab here. I don't know exactly what I'm getting into. I did cover a lesson in networklessons.com about MST. Okay, Callum, I think I need to spend another week on STP. Such a detail. It is, man. I keep trying to think of it as a routing protocol, you know? Like path selection and setting preferences and timers, and I mean, it's just got all the bones of a normal routing protocol, doesn't it? I literally have 2 physical switches connected. I still can't see agreement messages when using span. I think I'm cursed. Are you using span to capture? Is that what you mean by span? You've got a monitor interface running? Or spanning tree. Maybe that's what you mean. Like rstp, rapid spanning tree. You know what you could do, Callum, is... Oh, you're doing a local span. Right, on physical switches. What I could do is I could try to do it in GNS3 and see if I have the issue or not. Gotcha. Yeah, that's what I figured. Okay, local span monitor the rstp sync. Yeah, if you wanted to send me your GNS3 topology file, I could try it. We have the same images, and I have GNS3. You know, just for another pair of eyes to look at it. Because I think what happens is if you don't have agreement, I'm not sure what happens when you don't. I think you end up getting a lot more BPDUs being sent without the agreement happening, like the agreement state, the sync. Because the agreement flag is what lets the root switch know that the sync process is completed, I think. So if you don't have that, I'm not sure what the negative impact is. Because what I noticed is, for example, in this case, the other day, switch 1, sending switch 2, rapid spanning tree. Switch 1 is always going to send proposal flag BPDUs. But at some point, switch 2 is going to say, okay, I agree. I don't think that's such a big deal here. I think it is. Yeah, I'm not sure. It may not even be detrimental to not have agreement, to be honest. Let me look at that lesson real quick. What happens if you never have the agreement flag set? Is there a detrimental impact on the network? rstp. Okay, so agreement's important to transition to forwarding. So in other words, it is detrimental. Theoretically, switch 1, if we turn on rstp, he's going to send proposals until we get agreement from switch 2. He's going to withhold the forwarding packets on this interface. Once he gets his BPDU back with the agreement flag, then he transitions to forwarding, which usually happens very quickly. I'm going to span it from another switch. Maybe the span is just showing outbound to proposals only. Yeah, like I said, if you want to send me or I could lab it up in GNS3 and give it a shot. See if I get it to work. Maybe it's, who knows. Yeah, if I have time, I do that tonight, man. It's perplexing, I know. You're like, where are the agreement bits? Show them to me. I know they exist. But let's just talk a minute about multiple spanning tree. So I'm going to turn these off. And let me set this back. Let me put the environment back. You all. And on switch 2, Interface GI00, spanning tree. The spanning tree cost. Okay. What we're going to do here is, actually, what would probably work better is I'm going to add a note. Like I said, I'm experimenting here. I'm just going to put another switch. I'm just going to put another switch here. Need to get our switch numbers set up here. Switch 5. Yeah, I need to edit this guy, but anyway. What we're going to do is we're going to run multiple spanning tree here, and I'm going to create, we're going to have a total of 3 instances. So we're going to have an instance 0, which is common spanning tree. And then we're going to have instance 1 and instance 2, which would be like VLANs 5 through 10 and 5 through 9, and then like 10 through 15 or something like that. So let me connect these guys. And we're going to do, what's he got left? GI12, that's all he's got left. Okay, and we are going to boot him up. And I think what we're going to do is, so we're going to do our MST, we're going to configure VLANs 2 through 5 and 6 through 10. Then we're going to configure, let me do a new page here. VLAN 2 through 5, 6 through 10. 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's fine. And then we're going to do the MST configuration. Yeah, the interoperability part here is what's... so we're going to do, let's see, spanning tree, mode, MST, name, region, A, and instance 1, VLAN. Can I do 2 through 5? I think I can. Instance 2, VLAN 6 through 10. I'll just do through 9. Instance 1, 2, okay, and then we do... we're going to want to make sure the root bridge has a square head. What? So we'll do that on these 4 switches, 1 through 4. And we're going to make sure that on switch 1 that we want it to, well, it will become the root. These, by the way, these interfaces are down. And we'll say, yeah, just for simplicity, well, we only have 1 port available, so switch port trunk incap.1q, port mode trunk, no shut. Same here at switch 4. Okay, so they should trunk. Here we go. All right. So let's go ahead and do this on switches 1 through 4. All right, this is not pasting. Oh, that's a problem. Copy. Direct clipboard. Oh, come on now. Come on. Okay, that's why. Yes, okay. All right, I did not like spanning tree mode, MST. There we go. I missed that. Spanning tree mode, MST configuration. Then we should be able to do this. There we go. All right, we have our instance 1, for example. We have priority, designated, blocking, all of them. Okay. Now notice whenever you use multiple spanning tree, it automatically enables rapid spanning tree. It still says MSTP here. It does not have the... Notice though we're using like rapid spanning tree terms here though. For our port types. And if it has parentheses STP, that means that, oh, that's running classic spanning tree protocol, right? Okay, so let's configure the other switches. That's a little buggy. Copy, paste, there we go. All right, what are we missing? Spanning tree. Okay. Spanning tree MST configuration. Copy, paste. Copy, paste. There we go. Thank you. Yeah, they're not happy when all that's different. Okay. This should converge pretty quickly. Which it did. We even have a backup port. GI13. Okay, the host, what's going on with our host? Show run interface GI13. Unblocking. Okay. Blocking GI, inconsistent port type. Spanish tree port fast. Oh, it changed it for me. Edge. Okay. I just had port fast on there. Wow, and it changed it for me. That's cool. Well, maybe not. GI13 should not be receiving BPDUs. Why would it be receiving BPDUs on GI13? All right, I'm going to shut that down. That's weird. All right, that should take care of that. We don't need this host really for this particular lab, and we don't need the interface flapping. All right, so let's see what's happening here. VLAN GI12. Show interface trunk. Native VLAN 1. VLAN is a spanning tree forwarding state and not pruned. 1 through 9. Okay. So we have a trunk with GI12. That's good. I don't need you anymore. Goodbye. Okay, so as we can see here, we're running the old classic spanning tree, right? Oh, it has all these other interfaces on that we don't need. That's why it's acting strange. Interface range, GI 0, 0 through 3, GI 1, 0 through... There we go. Okay, single port, it is a root. We're good to go here. Now, we're running classic spanning tree protocol here. So this is what I wanted to see is how multiple spanning tree acts. Supposedly, the way I understand this is viewed by someone running spanning tree protocol when it looks at another switch running MST will run backwards compatible. And you really need to ensure that, and what happens is the MST region looks like a single switch, even if you have multiple connections. Let's actually do that. Okay, GI13, can we do that? Yeah. This is weird. Don't know why it does that. Let's delete those. Ah, okay, we got some sort of lab issue here. It doesn't like that. Uh-oh, did I crash my lab? I don't know. All right, let's go with what we have. All right, so the root ID, he still sees, look at this cost. All right, so at least he doesn't consider himself to be the root, which is good. We don't want that. Let me reload this. This is very strange. Okay. Ah, there we go. All right, let's do this. Interface GI 1.3, switchport trunk, incap.1q, switchport mode trunk, no shut. Interface GI 1.3, switchport trunk, incap. Okay, so that should become a designated port, but it should go into, it should be alternate. Okay, let's do debug spanning tree. Events. And let's do debug spanning tree events. And is there a debug for multiple spanning tree? No. Okay. Debug spanning tree MSTP. Okay. I don't know if I want all. I do not want all. Let's do state. Let's do sync. TC. Sanity check. Why not? Errors. Boundary. Yeah, let's do that. All right. So now we do show spanning tree. Interesting. Bound. These costs go way up, don't they? So this is MST0, the MST1, and MST2. Okay. It's interesting. I'm going back to this. This is one of the first videos I ever did on stream. Okay, so what I should see here on switch 5. All right, that went into forwarding. Oh, okay, because he will have a better cost. That's good. This is a more direct path to the root bridge. Interesting, though, is that some of the cost information is lost here. Let's do some captures on both of these ports. And I'm going to take the interfaces down and then I'm going to bring them back up because I want to see how this negotiation works. Because based on what I've read, the MSTP, the multiple spanning tree region is supposed to look like just one big switch to switch 5. Okay, there's 4. There's 2. 2 and 4. Okay, so let's take these interfaces down. Let's do it on this switch. Okay, we're getting our BPDUs. I heard the root there. I have a new root port here. Wait a second. So it said GI13. And I heard it on GI12, right. Supersedes this. So what is 6? Oh, that's me. Yeah, that's my own. Cost 4, GI13 cost 4. All right, let's see what it got. STP. Okay, coming from the root switch, directly connected to switch 4, port identifier 8007. Okay, so it's going to choose based on the sending bridge ID is lower on switch 2. Originating VLAN. Okay, notice here though, we should be getting these for multiple VLANs. PVID 1. These are all 1, aren't they? That's the only active. What we need to do is create another port. We actually need to connect him here, don't we? Yeah. We need an active port on another domain to see those other, or VLAN domain to see those other BPDUs. So let's do GI0. What do we got? We'll do GI01. Show interface status. All right, so we're going to shut down that port. Actually, let's not. Interface GI01, IP address 192.168.5.1. No shut. And we're going to make that, well, we're going to put it on VLAN 5 over here. SGI01. We're going to make a real funky topology. Switch port mode, access, switch port access, VLAN 5. Oh, it doesn't have the VLANs over here. That's why. No wonder. VLAN 2, VLAN 3, VLAN 4. There we go. Now, okay, that's what I would expect. Combine forces. Okay. Start these up again. Yeah, I wonder why I was not seeing multiple VLANs here. There we go. And then 9, yep. Good deal. All right, this is all fine and good. If I look over at the upstream switch, P2P bound, PVST. Okay. Like, yeah, I'm connected over there, but he's running PVST, so we see that it's doing what it's supposed to. MST is backwards compatible. So the bridge knows it has to, generate BPDUs for all these different VLANs. 4, 3, 2, 3, 4, 5, 6, 7, 8, right? Whereas if we look over here, what BPDUs is he generating towards switch 4? Let's capture those. Let's say GI02. We really only need a BPDU for each instance. Yeah, multiple spanning tree. There's an MSTS extension here. There's a lot of stuff in here. Region, we got the config digest. Internal root path cost. Remaining hops. There is a hop count here with the CIST. That is something different about multiple spanning tree. It does use a hop count. It has the instance IDs here. Somewhere it should have which VLANs are being used. I think. No, I guess the mappings just have to match. This might be a good case to use VTP. Sorry guys, I missed your, comments here. Was not scrolling for some reason. Let's see, if the 3650 is a root, I see no agreement from the 2960. If the 2960 is a root, I see an agreement from the 3650. I think it's time to go to sleep now. Good luck with MSTP. Have a good stream. Thank you, man. Appreciate it, Callum. Sorry I missed your chats. Yeah, it could be a platform thing, man. I mean, it definitely could be platform related. I would not be surprised. Yeah, so every 2 seconds. So that's a lot fewer than what have to be sent over here, right? So this is a lot more efficient. What I'd like to do to try is see if we can blow it up by basically making switch 5 the root bridge. This should be interesting. So we're going to get a spanning tree VLAN 1 through 9, priority 4096. Yeah, this is going to be interesting. So let's look at I'm losing track of which one is which here. PVID. Okay. So now we have switch 5 sending BPDUs as the root bridge to the multiple spanning tree domain. And MST is, I'll give it a second to converge here. How long will that topology change go out? Well, whatever the duration is of regular spanning tree, right? So it could be up to a minute. This is a funky looking topology, man. I hope you don't have a topology like this in your production network. So we have a this is from switch 2 sending to switch 4. And he's saying the regional root identifier is switch 1. So he's still trying to tell the network that switch 1 is the root. Oh no, here we go. Root identifier is switch 5. The CIST bridge identifier, that's who is sending. And the regional root identifier is switch 1. Okay. Okay, we've got TCAs, and I think we finally stabilized here. So the question is, will our traffic, will it work? Let's say we put a... how can we do this? Let's put an SVI on switch 4. Received internal topology change. Okay. Weird. So let's say interface VLAN 5. IP address 192.168.5.4. And now I should be able to ping that host interface, ping 192.168.5.5, which is on switch 5. Or no, host. I should be able to ping this interface here. It should go here to here and back. Show interface VLAN 5. Oh, it's down. Ping 192.168.5.5. Show IP interface brief. Isn't that not up over here? It is. .1. Okay, switch 4. Yeah, I wonder if we have like a loop or something. Show IP interface brief. 5.4, VLAN 5. Show spanning tree VLAN 5. Running MSTP. Okay, so see here, we've got the root bridge is switch 1. So the root is going to go, it's going to go here, JAS02. Look at switch 2. Oh, blocking root port GI13. No wonder, inconsistent, inferior PVST BPDU received on VLAN 2. But he is the root. Yeah, it doesn't like this at all. This bridge is a root. Why is he blocking him? Let's see if we can look up this error. PVST sim fail. Is that just a virtualization issue here? PVST simulation on MST. Okay. This document describes the purpose functionality per VLAN manager simulation on MST. Right. It also addresses the basic rules that must be followed in order to avoid PVST simulation inconsistencies and the reason for these inconsistencies. This is what I thought I might run into here. All right. I think what I'm going to have to do, folks, is leave the lab here. And we're going to need to go through this and see how to fix this. But we may leave off here. We may leave off here with a broken spanning tree. I hate land your head is transparent, possibly loud and can see through your head. Oh, okay. Man, I hope you can't see all the thoughts I'm having right now about multiple spanning tree. Thank you for the feedback, though, man. It might be, let's just remove that. See if that helps. Might be bright. But yeah, we've got a broken spanning tree, and so we're going to have to research this some more. Go back to the drawing board. I thought this might happen. You know, I may not need these headbands anymore, mentors, with the new LUTs filters. That's the whole reason I was doing it. Yeah, bandana clear. Yeah, it's weird, man. The green screen. This green screen will do green or blue. I can do different chroma keys, but it's a never-ending sort of shifting battle. All right, so going back to our lab here, assumption is everything worked fine as long as the MST root was the root for all the VLANs. Once we made the classic STP switch, the root, that's when we had chaos. And I wanted to, this is kind of what I wanted to happen, to be honest. So anyway, that's cool. I want to go see how to fix this and why it's happening. And, you know, we'll figure it out. Probably come back to this tomorrow on the tomorrow night stream. But I'm about to grab a little bit to eat. I want to thank everybody for stopping by the stream. Hope you enjoyed it. It's been fascinating stuff working on the spanning tree protocol. And I think this is kind of the last. I was hoping to be into layer 2 multicast by today, but I've run into, you know, a couple things with spanning tree, and I figured we'd hit a snag on MST interoperability with PVST Plus, which we have. So I'm kind of looking forward to actually playing with this, and we'll probably do that tomorrow night on stream. Thanks for stopping by, folks. I'm going to call it here and wish everybody, I'm going to send everybody good bits watching the stream. Enjoy the rest of your evening, and, you know, I hope you are able to get some more done, whether you're doing labbing, whether you're doing studying. You know, it's Monday, so you definitely want to get a good plan in for the week. You know, what you're going to target this week, what you're going to try to get done this week, progressing towards your cert. So wish everybody the best, and we shall see you. Oh, yeah, if you want to follow me, you can follow me here on Twitch. Hit that follow button. You can also follow me on YouTube, where I upload these streams. I also upload from time to time original content straight to YouTube. So definitely check us out on YouTube. Also Twitter, Instagram, GitHub. And of course, if you got a Twitch Prime sub sitting around or want to renew it, you can use it for free here at my channel. Hit that sub button. Thanks so much, folks. We shall see you back here tomorrow night. We'll grind again, as Mentor says. Hit that daily grind, and we'll see you back here tomorrow on the Land Tamer stream.